two more videos in this section. They're pretty relaxed. So we've talked about the normal model for continuous, unimodal, and symmetric distributions. It's the bell curve. We use it a lot for a lot of physical quantities and descriptions of nature. But now what if we want to compare events with different models? Like say, in our example, how can we compare the likelihood of rainfall in Portland with wind speed in Chicago for a certain year? Okay, well, what we're going to do is we're going to measure their standard deviations and talk about how far a value is in terms of standard deviations. Remember that every time we drew one of these pictures, we'd always just count standard deviations, and that would tell us how far we are. And we're going to formalize that notion with something called a z-score. A z-score is just how many standard deviations it is from the mean. So if something's 3 standard deviations away from the mean, well, we know it's really unlikely. Something's only half a standard deviation below the mean, it's still close to the mean, it's going to be pretty common. That's what we're doing here. We'll find the z-score, which again is how many standard deviations away from the mean. Standard deviation is sigma. That's how we find it with this formula. So let's assume, yes, Portland, we still know it's the same Portland example. Yeah, I get it, Jason. And let's call that random variable x. But now we're also looking at a new random variable, y, which is the average wind speed in Chicago. And that average is 10 miles an hour with a standard deviation of 2 miles an hour. Windy City got nothing on Southwest Wyoming, I gotta say. Anyway, suppose that one year, Portland's annual rainfall was pretty light, only 24 inches, and Chicago's average wind speed was 13 miles an hour. What was more out of the ordinary? What was more extraordinary? What was further away from the mean? We will do this with z-scores. So, we know Portland, x, normally distributed with a mean of 40 and a standard deviation of 8, whereas Chicago, y, was normally distributed with a mean of 10 miles an hour and a standard deviation of 2 miles an hour. We had one specific event of 24 inches of rain and one specific event with 13 mile an hour winds. What is more extraordinary? We will use this. All right. So here's our mean. Oh, I should stay in the right color. Here's our mean. Here's our standard deviation. And there's our x. Then we know that the z-score, how many standard deviations above or below the mean it is the x value minus the mean divided by the standard deviation. Now be very careful when you use this formula to follow order of operations. If you do it by hand, it's relatively straightforward. And if you use a calculator, just make sure to use parentheses. That's not my calculator. If you use a calculator, make sure to use parentheses of 24 minus 40 and the parentheses divided by 8. And you can get the same answer either way. Okay? The z-score is -2. What does that mean? That means that this event is 2 standard deviations below the mean. Below the mean. That's what the negative represents. Negative means it's below the mean, to the left of the mean, just like the number line, right? On the number line, -2 is to the left of 0. So pause the video and try to do these calculations. Find the z-score for Chicago. You should get, okay, x is 13 minus the average is 10 divided by the standard deviation is 2. You could either type this into a calculator or do it by hand. And you should get that this has a z-score of Here, we are 1.5 standard deviations above the mean. So for this problem, we're just comparing what's farther away from the mean, what's more extraordinary. So in terms of likelihood, normal distributions are symmetric, right? They're the same on the left and the right. If we were asking about what's bigger or what's smaller, the direction would matter. But we're just asking what's farther away. So we have to look and say, okay, if we have a normal distribution, what's rarer? 2 standard deviations below the mean, or 1.5 standard deviations above the mean? What's further away from that middle? And the answer is going to be 2 standard deviations away from the mean, right? 2 below, more extreme, further away, than 1.5 above. It's further away. So Portland's situation is more extreme. That's all there is to it. That's what z-scores represent. Z-scores are just how many standard deviations above or below the mean you are. This is our answer. Let's summarize this. So standard normal models are specifically normal distributions with a mean of 0 and a standard deviation of 1. So anytime we write Z, capital Z, we're usually going to be referring to a standard normal distribution. Z is always normally distributed with mean 0 and standard deviation 1. Okay, that's why sometimes I call it the standard normal curve. You don't have to write this down. This is not official. This is just Jason silliness. But it helps you to remember, maybe. Standard normal, okay? So we could, graph the model. 0 is always in the middle. 1 standard deviation, 2, 3, -1, -2. It's really easy to draw the standard normal, which is why it's so nice, okay? And so now we could really graph, right? 2 standard deviations below the mean was right here. 1.5 standard deviations above the mean was right here. Yeah, you can tell which one is further away for sure when you graph it like this. All right, and that's standard normal. We'll do more practice with it in the next one. But let's just kind of clarify one more thing to end this video. So we standardized both x and y into a standard normal curve. That's what z-scores are all about. So something with 24 inches in Portland with this model is the exact same thing as -2 in the standard normal model. So we could have this normal distribution in 13 miles an hour, but that's just z being 1.5. So if you standardize something into z-scores, it doesn't change the shape of the distribution. It's still a bell curve. It does move the center around. It makes the center at 0. It does kind of stretch it a certain way because it always makes the stretching, the standard deviation part, 1. We won't worry about that too much, but it gives you a little bit of perspective. More examples in the next video. Best of luck. Bye-bye.